Okay. Let me start sharing my screen. So today we're gonna do some combinatorics problem. But first, we're gonna go over 2 of the questions from quiz 3. And the first one is problem 1. And I'm sure you all have read the question. So it wants you to use the induction proof to show that your P0 dot A sub n is equal to P0 for all n is greater or equal to 1. And we have the induction statement here. So let's first start with the base case. Show P1 is true. Just gonna write this based on the definition in the question. We have P0 dot A1 and that equals to P0 times your A1 is equal to, we're going to use this formula here, P1 plus A0, where we have our A0 is equal to P0. So substitute that in, we get this. And just by using the commutative property, and that's A, we switched the order of this two to actually make the form looks like absorption here. Okay? And we can just conclude that that equals to P0 by J. All right, the base case should be pretty straightforward. And for the induction hypothesis, we assume that Pn minus 1 is true. So let's write out what Pn minus 1 is. We have P0 dot A sub n minus 1 equals to P0. That's our Pn minus 1. And for the inductive steps, we show that Pn is true, assuming Pn minus 1 is true. So that Pn here An. And if we substitute the formula for An, it will give us, which is Pn plus An minus 1. Okay. And then we see, okay, now we can use the distributive to actually use P0 dot Pn plus P0 dot An minus 1. And that's using distributive. And we have P0 Pn plus, and you will notice that this part is actually your induction hypothesis, which is equal to P0. And that's by inductive hypothesis. And then if you take out the P0 and you do Pn plus 1, and this part, we can use the universal bound, which will give us P0 times 1. And this is universal bound I. Universal bound tells you that it's this one. P plus 1 equals 1. Okay? And the last step, I'm going to use identity. That's P0 with identity. And we're done with the proof. Any questions before we're moving on? No questions? Okay. And this one is problem 6 from quiz 3. So we're giving ABC 3 sets, and we want to use an element-wise proof to show that A intersects B equals C. And we want to show their subsets of each other to prove set equalities. So we want to show this. A intersects B is a subset of C first. Let XY belongs to A intersects B. Where we have X and Y both belongs to Z integer. And then based on the definition of the sets, we have X minus Y is equal to 2K since XY is in set A. And also X and Y is equal to 3L since X and Y is also in B, where you have K and L are all integers. Okay? And then you will notice, okay, now I can see 2K equals to 3L. So what do you notice about the L here? Anyone? So we have 3L equals 2K. And we know that 3 is an odd number. So your L must be an even number, has the formula 2m. Oops. Where your m is integer. Okay. And then you want to substitute this L into the equation x minus y. You have x minus y equals to 3 times 2m. And that will give you 6m. Okay, and then you can conclude your x and y is in set C. And thus, you proved that A intersects B is a subset of C. And you're done with the first part. And now we have the second part showing that C is actually a subset of A intersects B. Like always, we let x and y belongs to set C, where we have x and y are all integers. And then we have xy equal to 6n, where n is an integer. So right now we can rewrite 6n as 2 times 3n. And by closure, we can conclude that that is equal to 2r. And that implies your x and y is in set A. Similar, you can also pull out the 3 instead of the 2. You will get 3 times 2n, and that's 3r, which implies that your xy is also in set B. So since your x and y are both in set A and B, we can conclude that x and y is in the intersection of A and B. And thus, C is a subset of intersects B, and A intersects B equals to C. Okay. Any questions about this one? All right. Let's now moving on to the combination and permutation sets. So the first one asks like how many binary sequences of a length at most 5 have exactly 3 ones? So we're given the binary sequences, and we know that the length has to be at most 5. We also want to have exactly 3 ones. What does this tell you about the length of about the possibility length of the binary sequences?
From 3 to 5.
Yep. You can have length 3, length 4, or length 5. Because you want to make sure you have exactly 3 ones in the binary sequences. So which formula are we going to use for this problem? So we're probably going to do the rule of sum to first find out, okay, how many binary sequences are there of a length 3, and how many binary sequences are there for length 4, plus the number of binary sequences of length 5, and that will give us the final answer. So what formulas are we going to use to put in this 3 box? So let's first start with length 3.
Do you do do you do choose?
Mm-hmm.
So it'd be choose of 3 of 3.
Yeah. So this problem will be, you will use, it's also called a set problem. You use C, 3, 3. And it is unordered, and you cannot have repeats. Okay? And that will give us 1. And what about the length 4?
C 4 3.
Yep. And this will give us 4. Five.
C of 5 3.
Yep, and this is 10. So in total, we have 15. So we will have 15 number of different binary sequences of a length at most 5 have exactly 3 ones. Any questions about why we want to use combination?
You use pluses in between each because each set is disjoint, right?
Yeah. That basically like 3 cases. You want to consider all the cases.
And we use a combination because the order doesn't matter.
Yep. The order doesn't matter. The order means that no matter you like if you first pick the second spot, it's the same as your second pick the second spot. No matter like which one you choose first.
So if the order mattered, would we use a permutation?
Yes. And without repeats.
Okay, then.
Okay, so part B asks how many binary sequences of length 6 have exactly 4 ones?
6 choose 4, which is 15.
Yep, 6 choose 4, 15. So C asks, why do these 2 questions have the same answer? So I don't want to go in depth about this one, but here's the theorem that states that suppose we have C choose KK plus C choose K plus 1 K all the way up to C NK, which is equal to C N plus 1 K plus 1. And in this case, your N is 5 and your K is 3. This is actually one of the exercise on the textbook. Is exercise 42 on page 108. Okay. Any questions before we move on? Okay. So now let's do a question that the order doesn't matter and we can have repeats. So how many ways can 2 winners be chosen from a cast consisting of just 4 people, A, B, C, D, assuming that the prices are identical door prizes, and that the same person could win both? So the order doesn't matter, and we can have repeats. So we want to rewrite this problem in the form that how many unordered list of length blank can be made from the set with repetitions allowed. What are we going to put here?
Would it be lists of length 2?
Yep, because we want to have 2 winners here. We want to choose 2 people or 2 winners. We can't have the same people win twice. And from set A, B, C, D. Okay. So for a bag problem, you just want to remember the formula. Can anyone tell me? What is the formula going to use for a bag problem? You will use a C, it's a combination.
Is it n plus r minus 1?
Yes, and you want to choose R. So in this case, your N would be 4, and your R would be 2. So you have total 4 possibilities you can choose from, and you want to choose 2. And this will give you C. That's 5 to, let's give you 10. Okay, any questions about this one? All right, let's move it on. All right, this one, it says we have 5 cards dealt off of a standard 52 card deck and line up in a row, so order does matter here. And the part A asks, how many such lineups are there in which all 5 cards are all red? We know that as we have 4 suits, and each suit we have 13 cards. And among all the 4 suits, we have 2 suits that are red cards. So which give us a total of 13 times 2, which is 26 total red cards. And we want to know how many such lineups are there in which all 5 cards are all red. The order matters here, and we cannot have repeat. Which formula are we going to use here?
Permutation.
We're going to use permutation. And what we're going to put this 2 number.
26 and 5.
Yes, exactly. Because we want to choose 5 cards from the 26 red cards to make sure that all 5 cards are all red. And that gives us and that will give us how many such lineups. So, and this is equal to this big number. Oops. Okay. And now part B asks, how many such lineups are there that have at least 1 red card? Notice the word at least. So you can use the way that to use the rule of to use the rule of sums, where the first case is going to be you have 1 red card and 2 red card and 3 red card all the way up to 5, and then you add them together. But that would require a lot more work. So if you notice, at least in the question, you can use the rule of complement, which you will find out the total number of outcomes or lineups to draw 5 cards, minus that the possibilities you do not have a single red card. And that will give us at least 1 red card. So what are we going to put in these boxes? So this part means that all lineups if choose 5 cards. And this one means that lineups that does not have red card.
There is a question in the chat. It might be easier to. I think it's a notation question for what a lineup in a row means. So it might be easier to, let's see. It's like a set with 2, 3, 4, 5, and 6.
Sorry. What do you mean, like?
Let's see. Lineup in a row means it has to be like 2, 3, 4, 5, 6.
Yeah.
Not sure if it's an order question or a notation question. If you have clarification on that.
I think the lineup only means that if you first pick you would just put as the order you pick. You just line up as the order you pick, not from the smallest to the largest.
So follow-up question. Oh, never mind.
Okay. Is that clear? Is that clear?
Yep.
Okay. All right. So let's get back to this. Is someone like give answer in the chat about what we're gonna put numbers in this 4 spot? Zoe, do you see like any answers in the chat?
Nope.
Okay. So we have. So the first part is all the lineups if we just want to choose 5 cards randomly, and we do not care about the color. We do not care about like if they're in the same suit. We just want to choose 5 cards.
Oh, wait, sorry. There is an answer. Someone put 52-5 for the first permutation and 26-5 for the second.
That is correct. So 52-5 means that we just want to choose 5 cards from 52. And that's all the possible lineups. And we start to minus the lineups that don't contain any red cards, which is 26-5. 26 choose 5. Because we have 2 suits that are all red cards, and we have the other 2 suits that do not have red cards, which adds up to 26 cards that are not red. And I want to choose 5 from them. And right here, we use the rule of complement, and this will give us the number. I'm not going to read it. It's such a big number. Okay. So there's actually another way to do this problem, to do part B. Anyone know, or you want to share, you think of like another way?
Would it be like where you find all the lineups with 1 red card and then 2 red cards and 3 red cards and 4 and then 5 and then add them all up?
Yeah, you can do that, but that would be just require lots more work to do because you have 5 cases. Okay, So for part C, it asks, how many such lineups are there for which all cars are the same suit? So we have 4 suits. We have 4 possible suits to choose. And we want to pick 5 cars from that suit. Let's see, like, what are the possible lineups if we want to choose cars that are all from space? How do we denote that?
13.5.
Mm-hmm. Exactly. And that's only for you want to choose all 5 cars from space. And if you wanted to find out, like, what about the other suits, you can just multiply by 4 because it's the same for each suit. And this will give you the final answer, which is 6,017,760. Okay. And you have part D. It asks how many such lineups are there for which all cars are either the same suit or red or both. So we know it's right here, either the same suit or red or both. So we can do this, write that as the first part gonna be they are from the same suit, plus the possible lineups that they're all red. But remember, we can have overlaps with the summation, and we want to minus the overlap, which the lineups has to be both from the same suit and they're all red. So what are the lineups that they come from the same suit? We just did that in part C, right? That's just 4 times P13 choose 5. That's all the possible lineups if you want to choose from the same suit. And plus, they're all red. And that would just be the answer from part A. 26 choose 5. And when I minus the overlap, which both has to be from the same suit and are red. And what is that part? You would do 2 times 13.5. Because you have 2 suits are red. And you want to minus that. Okay. Any questions? So there's actually a way I just think of for let me see, for part C that you can use. So part C that asks like how many such lineups are there for which all cars are the same suit. So instead of using the permutation 13 choose 5 times 4, you can do, you have 52 cars in total. And you just want to pick a random one. So we have 52 options. And now whatever that car you choose, you want to make sure that the rest of cars are from the same suit. So you can do 12, you can times 12, and times 11, and times 10, and times 9. That should give you the same answer as in part C. That's another way to find out how many possible lineups if they're from the same suit. Any question? Okay, no question. We're just gonna move on. All right. The next one is counting dice. So there are 6 to the power of 4 equals 1,296 different outcomes from rolling 4 distinguishable 6-sided dice. And how many of this is the sum of the dice 12? So we have 4 distinguishable 6-sided dice. So let me just draw a 4 box here. And we want to make sure that the sum of them equals to 12. If we name this as x1 and x2, x3 and x4, and we know that our xi has to be greater or equal to 1, and it has to be less than or equal to 6, since it's the number of the 6-sided dice. Okay. And we generally know that to found such questions, to found like the how many possible solutions are there to this equation, well, we generally use the formula for bag problem, which is n plus r minus 1 choose r. And in this of the case, your n would be 12, and your r would be 4. Sorry, it's the other way. So your wait, let me think. Yes, your r should be 12 and your n is 4. So, but we cannot directly apply this since we have a limit here for our x. This this will give you all the possible outcomes, no matter what x, no matter the value of the x. So the x can be 0 or x can be greater than 6. So we have to do some arrangement to find how many outcomes are there. Since we know that your xi has to be greater or equal to 1, which means like all these x's has to be greater than 1. And we can come to the equation that we have x prime where your xi minus 1 is equal to xi prime. Does this make sense? Okay. So now this equation, the solutions for this equation make sure that all your x are greater than or equal to 1. So we have 8 plus 4 minus 1, 8, and that will give us 11 choose 8. And that's 165. But we're not done yet, because this only that guarantee that our x is greater or equal to 1. But we also want to make sure that our x is also less or equal to 6. So which means we probably need to use this number to minus the outcomes that your xi is greater or equal to 7, which means your x prime I is greater or equal to 6, since your xi minus 1 is equal to xi prime. Is everyone still with me here?
There is a quick question. Why are we using the formula for unordered lists? I thought order mattered in this problem since the dice are distinguishable and the problem states that the total outcomes are ordered lists.
Yeah, so I think that in this question, we're assuming that, well, the order doesn't matter. Yeah. So I think right here I think it's a good question. I think in this one, we just want to assume that if the first dice you have a 6, and this, well, not 6. The first die you have a 5, and second die you have a 5. I think it means that the order doesn't matter to the solution, because 5 plus 5 is the same as you reverse this 2. I think the solution wants us to follow that they're the same. But yeah, so let me think. Yeah, I think the right here says only for distinguishable 6-sided dice. This part is kind of misleading. Let's just ignore this. We just have 4 6-sided dice, and they're the same. Yeah, sorry about that. And the repeats, and we can have repeats. Is that like answer your question?
Yeah, that sounds good.
All right, and then there is another question about is it C11.4 or C11.8?
It's C11.8. So we have this equation here. This one. And we know the our n is, we have n possibilities, which means that we have n items, or we have n spots to choose from. So our n is equal to 4 in this case, because we have 1, 2, 3, 4 spots to choose from to place our dice. Yeah. And we want to choose 8 to make them the sum is 8. So in this case, your R is equal to 8. We wanted the sum of these 4 types to be 8. So it's like you have a bag problem and you have 4 types of fruits. And you want to total choose 8 fruits from these 4 types. And your x1 and x2 and x3 and x4 are the how many numbers of each type's fruits you're gonna choose. Does that answer your question?
I think so, yeah.
Okay. Any other questions?
Hi, I have a question about when you come up with the formula. I have the same question in the Piazza. I think I posted, but because the thing is this one apply for the non-negative, right? The non-negative. So it's like if it's greater than 0, we already subtract 4. But in here it's greater than 1. So even that means we have to subtract 4 more because the formula original one is like greater than 0, right? And we switch it to greater and equal than 0, and now greater and equal than 1. Then that's supposed to mean like 12 plus subtract 8. So this one gonna be 4. The x prime, x1 prime plus what? x2 prime.
So yeah, so we have the first equation x1 plus x2 plus x3 plus x4 equals 12.
Yes.
This one implies that all x's are greater or equal to 0.
Oh, okay. Because I thought that one applied for the xi greater than 0, not equal. Okay, thank you.
Yeah. So there are non-negative solutions.
Mm-hmm.
And yeah, right here.
Before when I asked the question, it say that just the non-negative. It just means it greater than 0, not equal. So yeah, I got it now.
Okay, cool. Yeah. So and now we have the limit for xi to be between 1 and 6. So we want to show like they have to be greater than 1, greater or equal to 1. So we just minus 4, add it in and give us 8. Okay. And right here we have this. We found out that our xi prime has to be greater or equal to 6. And in fact, that if you look at this equation, your 4 xi prime add up together equals to 8. Basically means that you can only have one x prime that is greater or equal to 6. Otherwise, you will get a solution that is way larger than 8. Probably greater or equal to 12 something. Okay, because you can only have one x prime to be greater or equal to 6 in order to make your sum to be equal to 8.
None of them can be 6, right? They have to be like 5 or less for the sum to be 8 in this case.
Well, only one of them can be greater or equal to 6.
But there's 4 of them, and none of them can be 0, right?
Yeah.
So if one of them was 6, then another one would have to be 0 for you to get a total of 8. Unless
Well, it can be 0. Because
oh,
right, x prime is, we already subtract 1. So they can be 0.
oh, okay. Yeah, that makes sense.
If your x1, if your xi prime is equal to 0, that basically means your xi is 1.
That makes sense. Thanks.
Yeah. So, okay, so let's go back to, since we can only have one x prime that is greater or equal to 6, that basically means we can have 4 options. Because x1 prime can be greater or equal to 6, or x2 prime, or x3 prime, or x4 prime. And that gives us 4. We also need to times 4 times that. We're going to use the back problem again, which is, so if we have, okay, let me scroll down a bit. So if we have one of the xi to be greater or equal to 6, that basically give us the xi prime plus x1 prime, x2 prime plus x3 prime plus x4 prime to be equal to 2. After we do the 8 minus 6, because one of the x prime has to be greater or equal to 6. Okay. And now we can just compute how many solutions are there to this equation, which is we have 4 plus 2 minus 1, choose 2. Okay. And then this will give us C5, choose 2. And this is only one of the possibilities that if your x1 prime, if this one is greater than or equal to 6. And it should be the same possible outcomes that your x2 prime is greater or equal to 6. So we have to do 4 times C5 choose 2. And this is all the possible outcomes that your xi is greater or equal to 7. It's the same as your xi prime is greater or equal to 6. And then you will use the number we found here. Oops, what is going on? Okay, the 165 here to minus this. So you would do 165 minus 4 times C52. And this should be your final answer for this problem. And you should equal to 125. Okay. And I think that's all for today. Any last minute question if you want to ask? Okay, I think that's it for today.